Uh, Hello and welcome you all to the session of Applied Thermodynamics. So, as per your syllabus, the code of this subject is PCAUE, PCAUE 301. So, we'll be dealing with this applied thermodynamics. So, this is the first lecture of the planned lecture sessions of almost 36 planned lecture sessions. So today we'll be dealing with the introduction. So this is the introduction part, which mm, which where we will know how does thermodynamics affect our daily life. Um, I am Arindam Mukherjee, Assistant Professor of Automobile Engineering Department, Dr. Sudhir Chandrachud Degree Engineering College, which is under the JIS group. So let us start with it. So actually, what happens? Thermodynamics is basically mm, a collaboration of two different words. It comes from uh, I hope you are understanding what I am writing here. It is therm, T-H-E-R, T-H-E-R-M-E. So therm is a Greek word which means heat. So it is nothing but heat. It is nothing but heat. And dynamic or dynamics means force. So we know that uh, we do know that whenever forces is applied to a certain body or a certain system, some changes happen, and because of the application of force, some energy interaction takes place. That means some work is done, or work is done by the system, or some work is done on the system. So we'll be not going into that parameters now, but to introduce thermodynamics, it is a collaboration of two different words, therm and dynamics. So heat being the input force, how does it change the state of the matter? So this is what we are going to study here. So the application of heat on a certain body or a certain system. Okay, and then we can also define thermodynamics as the branch of science which deals with the energy and its effect on the matter. So we know what does matter means. So we are talking about some certain systems which is composed of matters. And if energy transfer takes place, predominantly heat in case of applied thermodynamics. So thermodynamics is the branch of science which essentially deals with the effect of energy on a certain quantity of matter. Okay, so this is the basic definition of thermodynamics. Actually, we live in the sea of thermodynamics. So most of the application which we observe, which we feel every day, consist of thermodynamics. Like here, you can see the example. So this is the human body. So every heat interaction, every thermal feeling we have can be explained by the help of thermodynamics. So if you are feeling hot or if you are feeling cold, so this can be explained by thermodynamics. The place where you live is connected with a AC system, or most of you will use a refrigerator in your home. The airplane is running in the sky. So everything you see, every electrical appliance you use is created, or it depends on the principles of thermodynamics. We can say the electricity is generated by the help of thermodynamics. So if there was no thermodynamics, electricity wouldn't have been generated. So you have to understand. So this is the perspective of thermodynamics. This is the applications of thermodynamics which we need to understand. And there is a very important thing which we must consider, is that the nature of processes, like the processes which I am trying to talk about is that, suppose in this there are some processes which occur naturally or spontaneously, like water always flows from high elevation to low elevation, like the river flows from high elevation to low elevation. Heat always flows from the higher temperature to the lower temperature. So this is the examples. These are the examples of spontaneous processes which occur in nature. If we concentrate on this diagram here, a ball is rolling down in the downwards direction spontaneously. That means if a man is present here, and if he uh, so if a man is present here and he leaves the ball will naturally reach the ground without any other application of force. That means this is the spontaneous process which we are trying to talk about. But if you want to move the ball from here to here, then through this through this line you have to continuously imply a certain amount of force. For suppose it will take t time, so for the time period t seconds you have to imply that force. Or if you apply a certain amount of large force so that it can reach here. But still the thing is, this process cannot occur naturally. You have to apply some external force. So that means the example I gave earlier, that water always flows from higher elevation to the lower elevation, but the opposite happens also. We know in our household the water is pumped from downward direction to the upward direction, which is stored in the tank. So how does it happen? So that means the spontaneous processes will occur in a certain direction, but there will be some cases where the opposite to the spontaneous processes can occur, but you have to apply some external force. So thermodynamics is a branch of study which helps us to understand which process will occur in which direction, and it also suggests if the opposite of that spontaneous process can occur or it cannot occur. That means it helps us to understand the direction of the process. So this is the important point you have to understand. So direction, so direction, and we can say feasibility. So I hope uh, you will be able to understand these two things. uh, the direction in which the spontaneous So what will be the direction of the spontaneous process, and the opposite to the spontaneous process, is it feasible or not? That are the two aspects of any process which has to occur in our in the which has to occur thermodynamically, that can be defined by the help of thermodynamics. So thermodynamics helps you to understand the direction of process and the feasibility of that process occurring in the reverse direction. So see, there is an example. A ball is moving downwards. The ball is moving downwards. It is obviously spontaneous, because if we apply a certain amount of force, the ball will move downwards. But to make the opposite happen, you have to apply a certain magnitude of external force. So this external force has to be either it should be in large magnitude, or it has to be applied continuously. So that means the external effect is the most important factor here I am trying to address. Here there is no external effect. It is occurring naturally. But to make the ball move at the top, here you have to apply some amount of external force. So this subjects will discuss later, but the most important thing which thermodynamics helps us to understand is that the direction of the spontaneous processes, and the possibility of occurring the same process but in the reverse direction. mm, so that is the point, the feasibility, which I am trying to address for the last 2 minutes. Okay, so let us move on to a new thing. How do we understand thermodynamics, or how thermodynamics is studied? So basically it is studied from two point of views. The first one is the first one, or the common one, is the macroscopic approach, and the second one is the microscopic approach, or sometimes we call it as statistical thermodynamics. Ludwig Boltzmann was a pioneer of statistical thermodynamics, whereas Sadi Carnot, um, we can say Nicholas Otto, Rudolf Clausius, they were the pioneers of macroscopic thermodynamics. So this microscopic approach is called as statistical thermodynamics. Now, from the diagram which you are observing right now, you may have understood, or you can get a feeling about the microscopic and the macroscopic. So here, so these two, both these figures are the same thing. Suppose this is the matter. It has a certain mass, let us say mkg, and here this matter is composed of numerous number of molecules. So this is the individual molecules which we are observing here, and this is the totality of that molecules. We are observing it as a certain matter. Now, what will be the effect if we apply some kind of energy on it? So this, there will be obviously a change. This change can be studied from the point of view of molecules, or we can study the same effect from the macroscopic point of view. So when we make this study, the branch of thermodynamics which studies the change in the matter, which we can observe from our open eyes, or we can measure. Okay, obviously we can measure these things also, but uh, the point is, this is a macroscopic approach. Okay, that means suppose if we consider temperature. So temperature is nothing but the mm, average kinetic energy. So it is average kinetic energy of the molecules. So that means these molecules are moving with a certain velocity. If we calculate the average velocity of this molecule, that will be manifested as a temperature. So when the velocity of these molecules increase, we sense that the temperature of the body has been increased, which can be measured by the help of a thermometer. So that means these are the two different approaches from which thermodynamics can be studied. The first one, or the general one, or the common one, is the macroscopic, which we'll be studying through these sessions. And the second one is the microscopic approach, or the statistical thermodynamics, which is beyond the scope of your syllabus. So these are the primarily this primarily are the two approaches by which thermodynamics can study. So let us move on to the next part. Okay, the next part which we'll be discussing is called as the concept of continuum. So let us consider that this is a certain point on a system. So let us allocate this point as A. Now this A point, which is this can't be actually a point, but this is so small that we're taking it as a point. Now you know that, you understand that any point in a space will have some mass, and it will occupy some certain space. So this uh, this space, or let us not take this as point, let us take a certain area that will be easy to understand. So let us take an area dA which has a certain mass delta m, and take delta v as its volume. So this system is composed of numerous molecules, which we have already understood from the microscopic approach. And from the macroscopic approach, we are treating this system as it has a certain mass. Let us assume this system has a certain mass of mkg. So here, what is the difference? That in the macroscopic approach, we are treating the matter as continuous. Okay. Now, uh, let us define a ratio here, del m delta v. So we can so we can find this del m delta v value for each of the molecule present in this certain area. Okay, so if we get a average value of all the individual molecules, then we reach this value for this dA area. Now we define this delta m delta v as average mass density. Okay, so now let us try to understand, if the average mass density raises, if the value of this average mass density goes on increasing according to this graph, we see that up to a certain value, these two curves, they merge. Okay, so what can we understand from this graph? That if so it depends on this delta v. Now let us take this delta V value. Initially it is very large, so this is the dA area. So this is the area dA, and we are taking a point P here. Okay, so now see, we suppose that the volume is very large in the first case. Then what happens? The value of delta M delta V, since this is very large, the obviously the value of this delta M delta V will be very minimalized. And then if we plot the same thing, delta M delta V, with respect to the volume of the system, then we can observe that the average density tends to approach an asymptote. So these two curves joining here, they are termed as the asymptote here. Now uh, as delta V, as this delta V is increased, let us take delta V here. So as the volume of the system, or the delta V value, is being increased here, we see that the average mass density, or delta M delta V, are reaching a asymptote. They are approaching an asymptote here. Now, so when delta V becomes small, that it is containing relatively very few number of molecules. Now this is why I had made this point P. Now we are certain that this point P will certainly allocate, there will be the number of molecules associated will with the point P is obviously less than that of the area of dA. So when we are concentrating on the point P, so that the number of molecules are very very less, we can see that the average density fluctuates. The average density fluctuates with time, as molecules, they pass into and out of the volume in random motion. So uh, it becomes impossible to find a definite value of delta M delta V. The smallest volume, we are taking this as the smallest volume here. So let us just clear it here so it makes easy to understand. So this V, or delta V, let us take delta V dash. So delta V dash is the smallest volume uh, when we can treat the matter as continuous, or the molecules as continuous. So then therefore we can define the density, and it will be defined in this way: the volume is tending towards the delta V dash value. So this is the minimum volume when we can treat this matter as continuous. So here lies the main concept of uh, continuum. So that means you have to treat the matter as continuous. Now what will be the smallest value, uh, where you can uh, what will be the smallest value from which you can treat this matter as a continuous? So here the smallest value assigned to this volume is delta V dash, and we can say density, or rho, becomes delta M by delta V here. Okay, so similarly we can also define the fluid velocity. We can also define the velocity. Let's say v vector. Uh, it will be uh, it will be obviously the instantaneous velocity of the center of gravity of the smallest molecule or the smallest continuous volume delta v. That means if the smallest continuous volume delta v dash moves with a velocity v, then the whole mass will also move with the velocity v. That is the point I am trying to make. And so you have to always find the minimum range where you can treat the matter as continuous. So that is the point of view, and that is the main concept of continuum. Okay, so now we'll be discussing how do we, so we'll be discussing the primitive steps of thermodynamics. So here you can see systems and boundaries. So this is the so so this is the foundation stone of thermodynamics. You have to understand it very carefully and very minutely. Now we are just entering the bridges of thermodynamics. So we have uh, told you that I have told you that the interaction of energy on the matter is studied through the help of thermodynamics. Now, uh, our attention is focused on that certain quantity of matter. So, all our attention is focused on a certain quantity of matter. So, this certain quantity of matter can be defined by a simple diagram like this. So, the space of the matter upon which all our concentration is focused is called as the system. That means what concentration or what focus? We are focusing on the energy interaction. Suppose for a very large device, we can observe there is a certain space where all the energy goes in and it comes out. So if we create a diagram of that space, then that will be our system. Suppose uh, let us take this as a piston cylinder arrangement. That means this piston, if it suppose there is a certain amount of gas or liquid present in it, so this piston can sorry this piston can exert some amount of force into this liquid or this gas. So this, this area, this space is our area of attention, and this will be called as the system. So all the space external to the system will be termed as surrounding. So system where all our attention is focused, and everything external to the system is called as surrounding. Now from now how can we distinguish system from the surroundings? By the help of boundary. So here comes the importance of boundary. Okay, so this is the boundary by which system and surroundings are distinguished from each other. Now this boundary, um, generally you will see this boundary is a rigid one, but uh, we'll also observe there are some flexible boundaries where these boundaries uh, can change also. Okay, So boundaries doesn't necessarily need to be rigid. It can be flexible also. Now, these systems can be of three types: closed, open, and isolated. So we'll be discussing these three systems one by one. So let us just write me. So closed, open, and isolated. So here you can see an example here. So what are the point of views from which we differentiate between these three systems? It is very simple. You have to understand the flow of mass. You have to take into consideration the flow of energy, and you have to uh, consider the concept of identity. So, these are the three factors from which you can distinguish three different systems. Now, the system which is closed to mass flow, that means here you can see no mass transfer. So it is quite eminent from this diagram that for this system there is no mass transfer allowed. That means we can also term this system as control mass system. That means the mass is fixed. There is no change going to happen for this closed system or the control mass system. Okay, that means for this system only energy can cross the boundaries, but no mass can. Okay, so for those systems where energy interaction takes place but no mass interaction takes place, that can be termed as closed system or control mass system. Okay, C for control mass system. So closed and control mass are synonymous. And now, from the point of view of identity, if the mass remains fixed, then the space it is occupying, it is not going to change. So if the matter doesn't change is its occupying space, then we'll see the identity will remain fixed. So there is no change going to happen in its identity. So for closed system there are three things. It can be called as control mass system. Energy interaction can happen here. No mass interaction happens here, and it has a fixed identity. But for open system, both mass and energy are allowed to move in or move out. Okay, and since the mass changes since the mass changes for open systems, we can obviously say the identity is not going to remain the same. So it will have a, variable identity. And so if the mass changes, then what is the area of focus? How do we focus on this system? How we can focus on the system? By focusing on a certain amount of volume. So in the previous case, that means in the case of closed system, where the mass, where the space it was occupying, it was fixed, it was easy. So that is why we mentioned the word control mass. But here the mass is changing, so the uh,
what we can say, the area of focus also needs to be changed. So this is why we focus on volume rather than on mass. So you have to remember that for open system, the boundary can also change. Actually, the nature of boundary can be flexible for open system. So it has a variable identity because the mass can change, and we term this as control. I am very sorry for my handwriting. So it will be control volume. So I hope you will remember remember these terms: control mass, control volume. So control mass has a fixed identity, whereas control volume obviously has a variable identity. So if now we will be considering a system where which is exactly opposite to the open system. That means if we think of a system exactly opposite to the open system, it means that no energy or no mass transfer is allowed for this system. That means there is no energy interaction or mass flow into or out of the system. Such type of system is called as isolated. So it is isolated to both energy and mass transfer. So isolated to energy and mass transfer. So let us remember transfer. This transfer word is very important because we can't calculate energy. We can only measure the changes. So you have to remember that thing. Okay. So I hope that uh, the concept of systems is pretty clear to you. So now we'll be moving. How do you do we analyze the characteristics? So this is the initial state and this is the final state. These two states can be connected by a line. It can be a curved line, it can be a straight line, whatsoever. Still, and we know the direction of these states. That means state 1 has moved to state 2. So whenever we are connecting these two states by a line, it indicates a certain process, a certain thermodynamic process is occurring. So the motion of the states from a certain initial state to a definite final state is what we call as a thermodynamic process. Now these thermodynamic processes can be different. It can be numerous, like uh, uh, let us start with isobaric. Okay, so this is isobaric. Let us take isobaric. So this isobaric means that it is a process. Isobaric thermodynamic process means that it is a process where the pressure has remained constant. Now suppose, let us consider a process has occurred from point 1 dash to point 2 dash in this direction, which indicates the pressure has remained constant. So this defines what? It defines an isobaric process. Okay. If we consider a process here in this direction, like 1 to 1 dash, then it suggests the volume has remained constant throughout this process. This indicates isobaric process. Now if temperature remains constant, then it will be isothermal. Okay, so it will be termed as isothermal. So whenever there is no heat transfer allowed in a certain thermodynamic process, it is called as adiabatic. Afterwards, you will learn different properties like entropy, like enthalpy. Okay, so whenever entropy remains constant, it is termed as isentropic process or constant entropy process. Whenever enthalpy remains constant, this might be sounding Hebrew to you because you don't know yet. Still, whenever enthalpy remains constant, it will be termed as isenthalpic process. I am not getting into the details of these processes. We'll be moving on to the next part. So depending on the nature of properties, if they remain constant, we have defined some certain processes where some certain properties remain constant. Okay, so now we have defined any thermodynamic process, which is the change of state. So properties help. We had the properties which helps us to characterize the system. Then we had state, which is generated by the help of two independent properties. And then we had thermodynamic process, which is generating by the help of the change of state. Whenever the states of a certain system changes, it generates a new thermodynamic process. Now we will be discussing a, the concept of thermodynamic cycle, which is also a collaboration of these processes. Now here we have seen this graph already. From this diagram we can see this graph has been generated. Now let us assume the thermodynamic process continues. It is a what? It is an isobaric process. So it goes up to 3. That means the system is compressed. The volume was larger here and then it got reduced. So it is an isobaric compression process, and the states changes and the state changes from 2 to 3, and then it goes to, sorry, it would be a straight line here, so it goes up to here. Okay, so this is an isochoric process. That means the volume remains constant here. So now, so 1 to 2 was an, we can say it is an process where PV was constant. Okay, you know the diagram of uh, you know the Boyle's law. Okay, so P is inversely proportional to volume that generates such kind of curve. So PV is equal to constant, and here P equal to constant, and here V is equal to constant. So this is, if PV is equal to constant, then, and if it is an ideal gas we are considering, then PV is equal to RT. If PV is constant, then T is also constant. So whenever PV is equal to constant, we generally see that T will be also constant. Okay, so it is an isothermal. So I am just using the abbreviations here. IT, isothermal, and this will be IB, isobaric, because the pressure remains constant, and this is isochoric. Okay, so now see what happens. Now, if you concentrate on the diagram on the states 1, 2, and 3, we can observe three unique processes has been has occurred here. 1 to 2, where temperature was constant or PV was equal to constant, which is an example of isothermal process. And then process 2 to 3, which was an example of isobaric process. That means pressure was constant here. And then process 3 to 1, where volume is constant. Now look into the initial states and the final states. Now can you understand that for this thermodynamic graph or this curve 1 to 3, the initial state is exactly same as that of the final states. So that means it the whole process started from here and it ended up here. That means when we observe a collaboration of different thermodynamic process ending at the same initial point, it means that an thermodynamic cycle has been created. So thermodynamic cycle, the word is cycle. Cycle means the initial states and the final states are exactly the same. Okay, so in the upcoming lecture sessions we'll be discussing about the cycles a lot, because to so to generate power, which is the main motive of any thermodynamic process, depends on these cycles. Okay, so I hope these concepts of properties, states, processes, and thermodynamic cycles is quite clear to you. In the upcoming lecture sessions, we'll be discussing about the isobaric, isochoric, adiabatic, isothermal processes a lot more, and I hope you will be able to understand very minutely about these processes, about these different processes. Um, okay, I will end this first lecture